Good news. Good. So first I went back and I looked at the homework. I still haven't got time going through it. So it's going to happen next Tuesday. So it's not going to happen today. Second is because of that, I want to push back the exam by a few days. So it's going to be the Tuesday, the following week. Okay. So November 7th, I believe that will be. Give you guys enough buffer zone to recover and rebound. And re-energize, regrow.
I'm so happy for you.
All right? Because I think seriously that's needed, because then I can finish the lecture next Tuesday, exam Tuesday. Then the next Thursday, you guys have some time to study, and I'll be around answer questions.
So it'll be on the 7th?
Yeah.
Okay.
Then the Thursday, I will be here, but we're not going to have exam. I'll answer questions we have, because that will be more reasonable, I think. When we have finish the last lecture, I want to keep 1 week from that to the exam. Okay? That will be the plan.
What time do you think you want us to show up for that?
Hold on just a second. Yeah, Jonathan, what's the question?
I said, what time did you want us to show up for it?
It depends on you. So the exam will be similar scope. So if you guys feel we need a little bit more time, I recommend we start maybe at 8:30. So a little bit early. Then we can have 2.5 hours. Sounds good? Is this something we can all agree on? Okay, so now it's my tough part is I'll try to entertain everybody for the next 30 minutes or 40 minutes. We're not going to have a full length of lecture because you guys just took another, 2.5 hour exam. So what we're going to do today, and different from the last lecture, is today's goal, we're going to talk a little bit about how we actually now can link the phase diagram with free energy diagram. Those are two types of diagrams. Let me get a black pen. So everybody recall in the last lecture, we actually talked about two types of diagram. One, we plotted free energy, delta G, versus how much solvents or how much polymer you have, right? Then we also have type of diagram, which is instead of use delta G, we use the T, and we plot over phi. And those are two different type of diagram. So I'll give an example. Let's use the UCST example, upper critical temperature. So in this case, we call it phase diagram. And everybody, this is very easy. I think if you can show your grandpa, they can understand. As long as you label this is two-phase. So this is not mixed, right? They can read it. This is mixed. Because all you need to know is how much polymer you put in the solvents and what the temperature you do it. But other part we talked a little bit about is free energy, delta G, plotted with phi. This is from Flory-Hagen theory. We talked quite a bit about this equation. So delta G is related phi 1 log phi 1 plus n divided by phi 2 log phi 2 plus chi times phi 1 phi 2, right? So this will tell you this graph. So today's goal is to finally, we're going to link these two together. So the goal of today is to explain to you guys how we can use Flory-Hagen series to understand the phase diagram. Okay. And only thing that theoretically we don't know to construct the phase diagram is the chi. And this is something we don't know because this changes by different polymer. That's why different polymer, different solvent have different phase behavior. Because phi 1, phi 2 these are all fixed. You change the mixing ratio, it will change, right? So in the last lecture, we explained two important concepts. First is how to construct a delta G divided by RT versus X1 curve. So X1, Phi 1, there's similar scope. It depends on if you're mixing the solvents or if you're mixing polymer and solvents, okay? So we talked a little bit about that, right? So you can, if I give you a chi value, if this is a known for the polymer, chi equals to 0, 0.5, or 2.5 or something, you can easily construct this delta G versus X curve. Reasoning is, the only unknown is chi. If I tell you the chi, I'm sure everybody can plot this delta G divided by RT, in this case, with respect to what is value there. And in this case, it's symmetric because it's plotting against a small molecular solvent mixture. Okay, so we call it regular solution series. That's why they look perfect symmetric. Left and right, you can fold them together. And one of the important conclusions we reached in last lecture is to determine if your solution will be stable or not stable. What we need to do is to take a second derivative of delta G with respect to the phi. And we told you that will tell you the sign of this local shape of this curve, delta G. If your delta G is concave down, that means it will not be stable. Your solvent will choose, your polymer solution will choose to phase separate into two layers. It will be happy there because it's released free energy to somewhere, okay? And if it's somehow behave like this is locally concave up, this will be very stable because any fluctuation in concentration will be suppressed and will come back to where they start. So that means we're going to be in a state that we will have this. We will have the exactly solution where we start off. It's very stable. So now the question is, how do we determine if they will be stable or not stable? And we discussed about this particular relationship. So if we define the second derivative of delta G with phi, we can reach the stability limits or this binomial line. Okay? So the next question is, how do we understand this metastable state? We talked quite a bit about the unstable state. This is the second derivative of this black line, the blue line, okay? So you can see I drew a black line, a dashed line. This is to tell you if it's going to be below 0 or above 0. So you can see that we have a significant fraction is below 0. That means any data point between these two, in terms of volume fraction, they will not be stable, and they will choose to phase separate or evolve or change, not happy with where they are. They're going to complain and do things. So if you happen to be sitting on this particular point, second derivative delta Gm with respect to phi is above 0. So this point, if we draw a vertical line, this point is exactly matches there. So this crossover point is basically a second derivative equals to 0. It's defined by this particular point where my finger is pointing. And these are all going to be stable state. Okay? That's what we have taught everybody about in the last lecture. So this is how you should understand the phase diagram from what we have. But this only explains one boundary condition, which is this particular line, okay? But they didn't explain this metastable line. So we're going to talk a little bit about metastable zone first today, so which is I highlight in this pink color. And we will explain to you guys why there's a metastable and how do we understand it. So this is the same plot. this is the same situation we want to show. So in terms of we prepare a solution of a polystyrene at concentration x1. X1, you can think about this maybe 50%. And we told you that, guys, that if they are sitting in these concave down region, it will not be stable. Now I'm going to ask everybody a question. So what's going to happen to their solution? We know he's not happy. He wants to change. So where he want to go to? What is next phase will make it happy? So it will phase separate. Right? We have one constraint is conservation of mass. If you have phase separation, so some area will increase in concentration, somewhere will drop. But the question is, will they, for the phase, they're going to be 100% solution, 100% polymer, totally phase separation, or it will stop at somewhere in the middle. How do we get that? Everybody get the question? If I have, let's say, use example 20 milligram per milliliter polystyrene solution, will it phase separate into 1 milliliter of solvents, then 20 milligram of polystyrene sitting at the bottom? I see someone shaking the hand. Joseph, why you don't think it will totally phase separate?
Because then you have different masses. Is that what you were talking about? How you have to conserve mass?
No, in this case, the mass is conserved because we don't leave any polystyrene out of the system. You still have 20 milligram, right? Yeah. Amy?
It would just, like, so the points on either side of one of these tie lines are the proportions of mass, and so it would want to go down into the wells, but not back up. And in order to totally separate, it would have to go back up.
Ah, that's close to the ground truth. Is there some degree of mixing actually is favored, but it's just not going to be totally phase separate. That's going to create too much gain of entropy, right? Because you're creating two-order system. We talked about when we, at the very beginning, when they mix, there is some gain of entropy is liked by the system. So it turns out to be we just need to consider what is the lowest the system of delta G it can reach. Lowest. When they phase separate, how much delta G they can lose. The more the better. But if we lose something like totally to zero and here, this may not be the maximum loss of the delta G. Because if you need to lose to here and here, if you draw a vertical line, you start to gain entropy. So it's only possible if you look at any phase separation need to be happens on these lines. This is the composition, right? At composition x1, this will create this amount of delta G. So the lowest possible energy going from this point is going to be this much, so which my finger is pointing. This is the maximum delta G you can lose for the system. Why? Because I challenge you, draw any two dots on these lines. Can you find a point that will be lower than the middle point here? You can. Literally you can. Right? Let's use the example. If I phase separate into B, situation B, I'm going to create something high and low concentration, but I'm going to lose a little bit delta G, which is shown between my finger. You can phase separate into another combination. You can think about any combination. The lowest possible will be a tangent line of where it cuts the bottom of this black well and the bottom of this, a tangent line of this well, okay? The E is not exactly the bottom. So if I'm zooming really big, so we look at our curve look like there, then we have, I'm pretty bad at the drawing. It has to be barely touching. But if we reach here, so it will not be the lowest point because the tangent is going to be cutting slightly left. But this arrow is very small. So you more or less can assume it will be very close to the lowest point of here. Okay? But it should be slightly smaller than here. So this will be the lowest system. So these 2 points will be the absolutely lowest system. So if you have anything in here, you have the potential to be split into D and E because this is lowest system. But if you have a point is beyond B and D and E, let's say I have concentration right about here, let's call it D prime. Can I phase separate into D and E anymore? No, you can't. Because you can't gain masses to reach a higher concentration. So that means this will be the stable state, one phase. And anywhere between the B and D will be the metastable phase. Okay, everybody got it?
Can you do that again? Just between which ones?
Okay, so we talked about transition between the 2 phase, unstable state. Unstable is defined by second derivative G equal to 0. So anywhere, if it's bigger than 0, if it's negative, so if you think about this would be the second derivative equal to 0. So anything between B and C is definitely not stable. Doesn't make sense because it's pointing down. But this is concave up. So theoretically, any dots between this B, which is green, and D is the red, should be stable. That is true locally. If I only can, change my concentration or fluctuate very little, I should be still be stable. Just will get you really quick. But if you somehow fluctuate your concentration really large, you somehow shed a lot of your mass and somehow jump into here, you can still phase separate. But there is a big barrier you need to overcome. So that is in one situation you can have is you have a large fluctuation in the system. That's why we call it metastable. So locally, any dots, any concentration between B and D are happy unless they see the flower is greener on your neighbor's yard because they never see it. But once they see it, they will change. They want to make it a bigger phase separation to reach the lowest energy state between B and D. So if we look at this curve one more time, so that will be your point D. And this would be the B, okay? So anything between B and D will be the metastable state. Okay, Joseph, you have a question, please.
Yeah, so is B the inflection point where you have the parabola going
Right.
from concave up to concave down?
Right,
And
that's
so
correct.
Anywhere in between that inflection point and the actual minimum at D is metastable.
Yeah, you can say it's minimum, but to be more accurate, it's a tangent line, which is the straight line cutting, when it's barely touching it. So this is not going to be exactly minimum, but close to the minimum.
Okay.
So this will be metastable because it will be super happy locally, but if its energy actually can fluctuate a lot, they have one possibility is to shed to this, drop a little bit delta G to reach this line, okay? That's the only difference. So that's why we call this area is metastable. So I'm happy to give you guys a few more minutes because that's all we want to talk about today is the metastable state and why there is a metastable state. Okay, yeah.
And each of these is measured at a different temperature, and you just take those points and you graph them at different temperatures and give them.
You stolen my thunder. Yes, that will be the case because at each temperature, remember that chi could be dependent on temperature. So that's why your shape of delta G will change, and that will be, let me show you here. I jumped a few slides, but we're going to come back. So at different temperature, so for example, if you have 3 different temperature will impact chi, you would have different shape of delta G. So look at this black line. So this would be at a given temperature T1. But when you change the temperature, your delta G shape will change. So when I raise the temperature, my delta G dependence on the phi could change into this particular curve. And if I keep changing the temperature, your contribution of enthalpy and entropy will slightly change. So eventually, you will reach a always stable state. Okay? So this corresponds to in the phase diagram how we get T as the axis, because you can see this would be defining the edge of metastable. This will define the unstable states. So if we pick those A prime, B prime, etc., we can construct the phase diagram. That's how these are linked. Okay? The trick is at each temperature, you will have a different delta G curve. So this is one Amy asked about. So let's come back. So this is a chemical potential. It's very similar to what we talked about. It's just another explanation when you talk about chemical potential, how chemical potential is related to different concentration of the polymer, and why we can draw a tangent line to claim when you have phase separation, this would be the lowest energy state. So this is just one line, and in the next slides, we will show you this would be the line that defines the same chemical potentials for the whole system. So this would define the lowest chemical potential. This particular red line, okay? That's we call the tangent line intercept with our system. So in this intercept, your polymer's chemical potential will match from here and there. It's in a relatively stable state. So this point defines the binodal. This defines spinodal, which second derivative equal to 0, and lowest energy or tangent line defines the other boundary condition.
I don't really understand the chemical potential line and how you got it. Like what it means. And
Sure. So this is a line that when we take an intercept with each, so along this line, when we mix them, you would have the same chemical potential if in this state or in this state or in this state. So this is all similar for the polymer. That's what we were saying. But the important part is understand how this defines the binodal curve, right? This would be the binodal curve, because these are the two possible lowest energy state point you can phase separate into. Okay? So I kind of already showed all the data points. At a given temperature, so this plot should be T. At given temperature, how we get each data points. We just need to repeat what, at each temperature, how do we find the boundary conditions? We can get all these phase diagram. So that's how delta G and phase diagram are linked. And one last thing that we haven't talked about is critical point. So TC. TC is defined at highest temperature possible. You can still maintain phase separation. So it's a coexistence of single phase and two phase. Okay? So TC. And you can get it from the third derivative of phi 2 with respect equal to 0. Derive it 3 times, you will reach what the TC is. And we can do that based on what the delta G value is. And we can take a derivative and get all these values are. Okay? So I'll show you guys what the TC respond to in the next slides. Joseph?
In the bottom of that equation, is phi supposed to be to the 2 or to the 3?
No. This is when I convert slides, it actually always has a little bit of problem. So it's a subscript. it should be third derivative, right? So
Yeah.
GM. So 2 should be there.
Got it. Thank you.
Or you can just say partial derivative phi 2. Phi 2 is where the polymer, this
Yeah.
x-axis. So you basically third derivative of y-axis with respect to the x-axis. So if we do that, we can get the condition to get the metastable state. So if we take the second derivative, we will reach. We can skip all the details how do you do derivative, but this would be the one of the conclusion. How phi and n, phi 1 is a solvent's concentration, n1 and 2 is where the degree of polymerization for your solvents, and this is for polymer how it depends on the chi. So when this expression equals to 0, this defines your spin-noodle curve. Right? Second derivative equal to 0 is when you have concave up or concave down transition. So you can see we can rearrange it a little bit to get what the chi, when your solvent's chi would be at the spin-noodle limits. So you can see this tells you at what concentration, depends on what molecular weight you have. So in this case, if we mix a polymer, a solvent with a polymer, N1 would just be equal to 1. Phi 1 is going to be the solvent concentration of in this volume fraction, right? So this would be the phi 2, N2 would be degree of polymerization. So that would be the critical chi you need to reach. And one important part why we have different dependence of this phase behavior is because chi usually is a parameter related to the temperature. So if you have a handbook that you can get what is A value, B value, and we know this is what would be defined in boundary condition, we can calculate the phase diagram by looking at this temperature that defines the spin-noodle composition, spin-noodle line. Okay? So this would be rearrange the T to the one side and rewrite what is A and B with respect to phi and N. So that will define your TS. I think there will be everything. Oh, one more thing. So we can get what is critical temperature would be using a similar equation, and we can get the critical chi C. This we haven't talked too much. So this will tell you what is a critical interaction parameter would make it phase separate. So in this case, when you add different solvents, you can see if we don't have polymer, if we have both solvents, N will be equal to 1 and 2 will be equal to 1. So in this case, we will get chi would equal to 1 plus 1 will be equal to square divided by 2. Critical chi need to be above 2 to have any phase separation phenomena. So that's the minimum chi you would have. That's a chi C for here. So in this case, you need to have chi at least bigger than 2 to make it phase separate. Okay? But if you have a polymer, you will see the chi C will be significantly lower. Because when N goes up, think about a polymer has degree of polymerization about 10,000. This will be 1 divided by 10,000 root square. It's almost going to be 0.01. So very small compared to the first term. So your critical chi will be equal to 1/2 divided by 1 plus 0.01. So that means your chi C will be 0.5. That defines the critical chi that your polymer will phase separate in a solution. So in the polymer case, chi C would be roughly 0.5 for polymer solvent mixture, okay? So now if you have a polymer mixture, then this value will be very, very small. Because imagine your polymer 1 will be 10,000 degree of polymerization, polymer 2 will be 10,000. Your chi C is closer to almost 0. So if you have a little bit chi, it will phase separate. Yeah?
Can you go back to the previous slide?
Sure.
So I don't really understand what this chi S is for.
Okay. So do you, first let's go here. Do you understand this line? So if we take the second derivative, that defines the boundary point of binoodle. So when you're going to phase separate or not,
Yeah.
right? Because that's the boundary between the one phase or two phase. And we talked about concave up, concave down. It's all settled at second derivative of delta G equal to 0. And we know the delta G can be written in general in this term, N1, N2. This would be any generic polymer mixture, okay? So we can basically take a second derivative of this with respect to phi. In this case, phi 1. You can think about this would be y, x, 1 minus x, 1 minus x. So you can take a derivative. It will give you this conclusion. So at this conditions, you will start to have a spinoodle curve. Okay? So in this case, when it's set to 0, that's where it could have the phenomenon we just talked about. So if we have that equal to 0, I just move the chi to the other end, then leave these two terms here and divide it by a half. That's all we did. So we define what is critical value for the chi will make it phase separate. So that's the minimal chi you needed to have the system to have the ability to phase separate. So if chi is really small, if you guys recall, let me go back. When the chi is really small, we don't have anywhere would have ability to phase separate. Does that make sense? All your delta G curve will just have concave up. So in this case, because we use a solution mixing theory, so your critical chi is need to be above 2 in order to show up this region. So second derivative 2, maybe just a flat line look like that. If you have 3, 2, or 3.5 or 2.5, you start to be able to get second derivative equal to 0. That would be roughly here, right? That would be defined second derivative equal to 0 because it changed from concave down to concave up. If you have chi smaller than 2, it's always going to be concave up. That's what we were talking about.
So in order to get those wells, which leads to the phase separation behavior,
Yeah.
you have to have a chi greater
Yeah,
than 2.
that's what we are talking about. What is the critical value of chi we needed in order to have the system has ability to phase separate?
Okay, can you go back to the side of the equation?
Sure. Right. Okay.
Wait,
Did I pass it?
no, keep going.
Okay, I'm
It's,
wait, it's not here yet. We haven't talked. Okay, here,
yeah.
right?
Yeah.
That's what the chi critical is. And this is basically you can get from move the chi to the other end, then divide by 2 of these parameters. That would be phi 1 and 1, phi 2 and 2, or 1 minus phi 1. Okay, that's the critical chi. So in the next slides, this is an explanation of what is the critical chi C. And phi C, what is phi C? We haven't talked a bit about that. So that is what is the concentration of the polymer at the critical point. Okay, so the critical point is where this. So we know what the chi, but how about at what concentration? We call it phi c. So this is related to what is the composition you have in your polymer. So it's given by solving above equation, you will reach, it's equal to root square of n1 divided by n1 root square plus n2. So what's the physical meaning? Again, let's use a solvent-solvent mixture or regular solution theory. In this case, n1 will be 1, this will be 1, this will be 1. So what you reach is phi c will be equal to 1 divided by 1 plus 1. So that's half. So that's why all the regular solution theory, it's symmetric because critical concentration will be right at the center. Let's tell you what the phi c is. Phi c will be 0.5. But when you start to have polymer in solvents, your phi c will change. And will change a lot because your N1 is still small molecular, so you can treat it as 1. So root 1 again, this is going to be 1. But your polymer has much bigger N. So your phi c is no longer at 0.5. Let's use example of let's polymerization N equals to 10,000. If you take a root square, that's about 100. So this will be, phi c will be 1 divided by 100, or 1%. Okay, so your phase diagram will not be symmetric, and that's what you guys have seen in some of the example. This would be a phase diagram, more commonly in polymer. So this would be the critical point, right? That's the highest point you have. So you can have critical temperature this way. That would be what is Tc. And you can have the phi c this way. This tells you what is the critical concentration. So in this case, when we increase the molecular weight of your polymer, your phase diagram will shift. So when we keep increasing the molecular weight, your phase diagram will go from, it has a critical concentration from 0.1 to even lower. And I explain how this depends on, it all depends on phi c equals to 1 divided by 1 plus root n. So when n goes up, your phi c will drop, okay? That explains high molecular weight, you're going to have shifted to this region. This means it will be, at low concentration, it has more tendency to phase separate, right? Because at the very low concentration at this temperature, it will phase separate here, but not here in this case. So molecular weight has an impact on thermodynamics of mixing in this sense. This part we have already talked about, right? So this is just a generically, if you have a more polydispersed system, you would have a non-symmetric phase diagram and it's going to be skewed to a lower concentration, lower polymer concentration region, okay? Your boundary will no longer be well defined like a red curve, but instead you have a little bit broader range if you have a polydispersity in your polymer. Because Amy, this is low molecular weight, and this will be the high molecular weight, right? High molecular weight will shift to the lower phi c, and it's also going to shift to slightly higher temperature, critical temperature. So the boundary may not be that well defined. Okay, so I think that's pretty much all I want to say. So any other questions? This is a good summary slides. It defines the boundary condition, what is binodal, what is spinodal, and what is critical points. Okay, in this, at least in here, it's written correctly. Okay, so any question for me? Because that's the goal I want to do today, is to link these two curves and use Flory-Huggins to calculate a few critical points. So I think it's important for everybody to understand how to calculate phi c depends on molecular weight and can able to read the phase diagram of different polymers. Question, comments? Not much? Amy, please. I can rely on you, I know.
I still don't really understand what mu is. Like, I get that it's a tie line, but I don't know why we have an equation for it.
Sure. Let me go back to the chemical potential. So this is a chemical potential that basically, chemical potential in the fundamental sense is you need to have equal chemical potential in order for a substance to be stable. So let's say your chemical potential for the polymer in A, when they phase separate into two, it not only need to satisfy the conservation of mass, because in a beaker, when they separate into two layers, we don't add polymer there, so it's always need to be one, so phase separate, one goes up, one goes down. But also need to make the happy that in this particular polymer, your chemical potential in the high concentration and low concentration need to be matched. And how do you satisfy the chemical potential to be equal? It has to be on a straight line. It's a linear combination because chemical potential is directly proportional to the concentration of polymer. If it's still a little bit complex, happy to chat with you more offline. But that's everything I want to say about phase diagram. So in the next lecture and the last one, we're going to come down to a bit better understanding about this parameter chi. Because this parameter is a boss for understanding the phase behavior. Everything ties down to the chi value and n. So these two are very important for a polymer solution. So if you get the value of chi and you know the degree of permutation, you can construct a general phase diagram for the polymer in solution. We're not going to ask everybody to construct it, but at least you guys need to know a little bit thermodynamically what is fundamental behind it and why it is different between polymer, solvent versus solution mixing, okay? So with that, I'm going to wrap it up. I'll release you guys so you can have a good lunch and have a good break after the exam. All right, then we will meet each other again in the next Tuesday, okay? Next week. Sounds good?